So let's get started, and I'll start by introducing what the Square Kilometer Array project is. For those who do not know, we are basically building what some call it the telescope to end all telescopes, radio telescopes, that is. But let's just say it's a very large telescope across Africa. And that's an important characteristic of the telescope, in that the expanding out of South Africa allows us to put really long baseline. The further out two individual antennas are, the more we can resolve bodies in the sky with a bit of a trade-off on sensitivity, but the resolution improves. One of the things that allowed us to win this is that African partnership, where we were competing with Australia, who basically have a bigger area than South Africa, but not nearly as big as Africa. So that was so Square Kilometer Array, remember this, SKA Africa, not South Africa. So, and then the evolution of the project. A few people who worked on this project had worked previously on other projects that had mixed outcomes. So when they were asked, how would you approach this, then they said, no, we're going to go very model-driven. So they started with the XDM in SARAO, in Hartbeespoort, where they built their first antenna to prototype what became KAT-7. The KAT really means Karoo Array Telescope. It was a 7-antenna interferometer as a precursor to MeerKAT. Then somebody said, well, we need more KAT-7. What are we going to call it? And Meer is Afrikaans for more. So we ended up with MeerKAT as the name of a 64-antenna interferometer with an 8-kilometer baseline. Then in the future, in the near future, hopefully, we will go into the Square Kilometer Array project. The status of that project now is that in the next semester, we'll be going through what in systems engineering terms is called critical design review, where different components and the entire system is reviewed from almost like a requirements specification point of view. A couple of antennas for it have already been developed. One is sitting at site right now, being tested and engineered for RFI. But you get the idea. We are going ahead with this thing, hopefully. So the other question of the location. The telescope area is about 10 kilometers outside, 100 kilometers outside a town called Carnarvon in the Northern Cape. It's an isolated area, and we do want it that way, in that human civilization and in things like cell phones, electronics, cars interrupt the science. The area is preserved under a national act as a key zone, I guess, with the view that this has actually become a natural resource. The same way we would protect our gold, our water, we protect this radio astronomy zone. There's in Western Australia, it's where they do the low frequency antennas. So that's the other half of it. And then about 8 antennas for now. I think it's probably going to end up being more, are going to be across 8 African countries. Like I said, they're very important for us, those antennas. So that's basically the geography thereof. And then the African partner countries, as you can see, a lot of them are in Southern Africa, the islands, and then Ghana and Kenya. So now I want to introduce you or speak specifically about the MeerKAT. A lot of people talk about the SKA, but not enough, in my view, speak about MeerKAT. You see, MeerKAT exists. SKA is a wish list. It's a shopping list. It's like going to shop for a ring with your girlfriend. You're not even engaged yet. You have an idea that you'd like to get married, but you're not there. MeerKAT, on the other hand, lives. And it matters because right now they are when Phil Diamond from the SKA organization at the unveiling of this project, of the telescope, said, it is the greatest telescope on Earth. And I tend to agree on a number of factors. So some of the things that you would have seen, I wanted to get into the exciting part. This is a blob that we observed with the first 4 antennas. I can't remember what year it was, but I remember it was very exciting. Then we got into the haze of delivering on time, so it all got blurry. The first one is with 2 antennas. Then this was with 4 antennas. I think this was the beginning of 2016. And it's the same blob, by the way. You can see how much more it is resolved here. And then we're like, okay, it's 3 sources, interesting. All these lines you're seeing here is basically our inability, is almost the telescope interfering with the data you're receiving. So it's quite a low resolution. Yeah. Then this is with 16 antennas, but this 16 antennas were really close by. They were in what we call the core. But now you can see it's actually, you can actually see that, sorry, let me just go one back. You can now see that actually there's a source in the middle, and these are emissions. And you can see that background noise there is a little bit less wobbly and interesting, but it's getting clearer. Then you move into this part, then you can see actually how far the plume goes around the sources, and you can almost characterize it more. And that's the power of the telescope. What you see in space suddenly changes, and you can analyze it further. Clarity is everything, I guess. And now this is a place called the Deep 2 field. Now, we used to use this as a calibrator space in the sky. So you got an instrument, like any science instrument. You want to know that the measurements you're getting what is the performance of the telescope versus its design. You sort of shoot something you think you know. In this case, we thought you knew this. It was quiet, so very easy to resolve. And then you shoot what you don't know, and then you take the 2 to calibrate what you don't know, essentially. And we would hit the source until we hit it with 32 antennas. And then it turns out, oops, it's not that quiet. All these sources here are galaxies. You can see how many more. We resolved thousands of galaxies from where we thought we had 20-something galaxies. So, again, the power of the telescope reveals itself. Again, to background on the MeerKAT versus the SKA. MeerKAT is a South African project. It is paid by South Africans who get into taxis every morning to go to work, sort of. And so it's our, well, I wouldn't say it's ours, but yes, it's South African. 64 antennas go into it. It is an engineering project with capability to do science. So it is a science instrument, so to speak. It is capable, but so far, for the longest time, MeerKAT has been an engineering project. If you went into our organization, the majority of people there are engineers. It is a precursor to the SKA, and we did unveil it in July 2018. And then, as an engineering project, you can see it was broken down into its several components. At the top, level 5 is what you call the MeerKAT system. If you know anything about systems engineering, this is top-down / bottom-up kind of like view of how the system is configured. In there, we got 2 major groups. The one is called the MeerKAT infrastructure segment. These guys are essentially responsible for the site. They make sure that A, we have a site, B, we can get to the site, C, when we put things on the site, the lights will actually come on, D, it won't get stolen, and everything that goes in between that. And it's a lot. Then you got what you call the MeerKAT telescope segment, and that's where I fall in, technically. And in this space, you get antennas, structure subsystem. That's the so-called telescope that you see. The time and frequency references, the timing we use. Timing is important to us. Control and monitoring are the people who actually is the system that allows us to know what's going on and control the system. So one of the characteristics of MeerKAT is that we control it entirely from here in Cape Town. There's no telescope operations, so to speak, at site. If we could make it lights out, we would, but we're not there yet. But the idea is that the ratio of work being done in Cape Town and work done in Carnarvon in terms of science or control of the telescope is done in Cape Town. Then we have the science data processing system there. That's the one that I come from. And we are responsible essentially for drawing data coming out of the telescope and making those pictures I've just shown you. That's a very simple way of, but succinct. And then you got the RF system who basically route the data within the telescope and without the telescope. So, for example, this is work that would be done by the infrastructure system. These are the foundations back in 2014, 15, early. Yeah. And then that's the telescope subsystem, the receiver subsystem. You can see them, they've just finished the pedestal, they're gonna mount this thing, and then fit all sorts of things into both of them to make it actually work. I don't know, if you haven't been to site, please note that the ratio of these people to this pedestal. This adds another meters here. This goes literally up to 18 meters. It's quite an awesome experience when you get close to these things in the middle of what is otherwise a desert with lots of snakes. When you see this, when you get to the core of this thing, it's truly mind-blowing. It's like literally a still forest. It's a marvel. And then this is what I call the MeerKAT signal chain. So this is about what happens once you switch this thing on. I'm not going to talk about the engineering work. I'm not going to talk about the fiber that puts these things across. But light comes in, hits this reflector, which sort of concentrates it, hits this sub-reflector. And here is where your LNAs are. Per antenna, we have 4. So we can work on 4 bands, basically. It's an interesting thing because then typically you'd get 1 band per telescope. Here we have about capacity for 4, we have 3. And some people are pitching that maybe we'll get an X band, but that's for the future. And then, so once you do that, it goes into the LNA. Sorry, as I said, it goes into the LNA. And then from the LNA, it gets digitized. So that's another interesting thing about the antenna, is that we digitize at the antenna. Then we move digital signal out using switching and fiber. What is here labeled signal transport. It goes into a building there in the Karoo called the KPB. And in there is a subsystem called the correlator beamformer that basically take all this data, aggregates it, so that all these individual antennas behave like one telescope. Once it comes out of there, it goes into the science data processor. And you can see the timing and frequency reference actually gets added there, and we use it to refer so that we can phase the signals that we receive. And underneath all this, they're belied by the control and monitoring. Control and monitoring, for example, on this antenna alone, there's just about 800 sensors to check various things, including what shape each of these things is, what the temperature is, where it's facing, all sorts of performance issues around it. And that goes across all subsystems. If a hard drive dies at the CHPC, control and monitoring technically advises me that that situation is happening. So that's an animation form. You can explain the same thing to your children. So one of the elements that you don't see is the operators. The operators basically get given, and the astronomer on duty basically get given what to observe. They then prepare the telescope, observe, and trigger that whole value chain. It goes through, it gets qualified, and results are produced. All these guys are the triggers and the finishers of the process. And now the science data processor thereof. And I say get the SDP right, because that has been the only thing on my mind for the last 5 years or so. These are the basic components of the science data processor. We produce simulators and emulators because you can imagine this telescope doesn't exist. We simulate it as we go along. We have what we call the execution framework, which executes the science data processor. The science data processor is a chain of tools to get to the data. We have a data ingest, which takes in a few 100 gigabits per second. At the end of our process, we are looking at something like 20 gigabits per second. So it's quite a significant reduction process. And then we have a calibrator. We calibrate the telescope so that we can provide the science community with the quality of the data. We image. There's a thing called time domain. That's pulsars, if any one of you, or transients, if anyone knows of that kind of science. QA and commissioning, that's quality assurance. Commissioning is our ability to tell you what the characteristics of the telescope are at a given time or during a specific observation. It changes all the time. It's quite a complex instrument, affected by weather, affected by all sorts of factors. The science archive and visibility storage. So we have to store this data for future use, for reuse, for processing, and we do that in partnership with the CHPC. So if you look at the first image up there is at the KPB in the Karoo. That's our imager. And then the data gets transported out. Well, a little bit more gets done to it. But essentially, once it's done here, it gets transported out from Carnarvon all the way to the CHPC in Rosebank. That's a CSIR facility under NICIS. And then once it's there, it's stored, it's archived. We have about 24 petabytes worth at 50%. That's about 12 petabytes, backed up by another 20 petabytes in tape not in the picture. Well, actually, it is right at the corner over there. And then this is just the dashboard built in Grafana that we use to monitor our system, specifically our system. And then this is how the science processor looks like for those who are inclined to care for it. But the idea, if I want to take you through this quickly, is that this is the correlator. Basically, this data coming out of the telescope goes into the ingest, as I said, where one of the things we do, very important, is excise, what we call RFI. That's basically the data we do not need. We flag it, and sometimes we get requested to remove it, but that's where we build the tables of what is it that we do not need. And I'm going to qualify the statement of what do we not need in the future. Then it goes into the calibration nodes, which basically split the data to make sure that you get the calibration, and then we flag our calibration data. And then we input what we call cam data, because we need to get the tell state. Like I said, the state of the telescope matters. And then we go into imaging. And once we image, that's when we essentially send the data out of the Karoo to Cape Town. So that happens in the Karoo, this happens in Cape Town. It lands at the CHPC, where we have an interesting facility there. Let me move that out. So it arrives in the CHPC. We sort of have physical spinning disk that we write to, at about 20-something gigabits per second. That's the maximum capacity for now. We can max that further. And in there, we store it. So when somebody says, give me my observation, it's coming out of the CHPC. And this image here is one of the success images that has come since the unveiling. It is the Galactic Center, as they call it. I'm not going to go into it, but to contextualize it, the black hole is somewhere around there. And all these things are happening in response to the effect of that black hole sitting there. To give you the context of about where it is here, this is where that picture comes from. This is kind of roundabout where we are from an overhead point of view. This was taken with a nanosat that I sent out to space 3 years ago. I'm joking, this is an artist impression. We can do, yeah. And over there, it's a lateral view of where we are. So that's quite this is about 26,000 light years worth of distance between us and that image. And somebody, Peter from UWC, when he saw this image, I think literally on the day of the unveiling, put it in a context. You can't really see like this, but if you're really, really in a dark sky, you can almost see your Milky Way outside. And just to give you an idea of what the scale of what you're looking at over there. So I like this image because it just simplifies it for when my father asks me, what do you do for a living? I don't have cattle, so he doesn't really know how he feels. Comprehend the SDP again. So I've told you what the SDP is from an engineering point of view. But what it really is, the SDP is the tail of the telescope, so to speak. Everything ends up in the SDP. So if somebody at the LNA does something funky and it sort of gets away with it throughout the value chain, it's going to appear because the SDP tried to do something. So getting it right is quite important. It's where the science is going to be verified out of. All the promissory nodes will deliver science. If the SDP cannot get that data out to the scientists, and the scientists trust that data, we out. The whole thing is out, down the pit. Okay, maybe 10 years later, somebody will teach a PhD student about what not to do in engineering about it. And then that's not why we build it. So the science impact as well is quite important to us, which is quite ironic because we actually do not do science. We bring the data, our engineering specific, our contract with our scientists is that we will give you the data you need to do the science. However, you can imagine this becomes an unearthed facilities. Papers don't come out, or papers that come out do not have impact sufficiently. Then why did we do this, right? The public are really interested. If you hear about the MeerKAT narrative, it's never really about its sensitivity. It's always about like, oh, the data compared to iPods at one time, calculated in the size of the internet at another time. Matrices I don't really like, but really fashionable, and people cling to them. And they come, and those are the product of the SDP, essentially. It is the point of departure from the SARAO observatory as well to what I call the National Cyber Infrastructure System. So when you're here and they're talking about how they're building towards this national infrastructure, one of the issues there is the science processing for the SKA. Who is going to do it? Where is it going to happen? Who's going to host it? How is the data going to be driven? And that's outside the parameters of the telescope. And the SDP is literally the node that connects to this. So it's kind of like important. The user community, when you get data, as I said, out of the telescope, when you schedule an observation, when you apply for time, you're going through the SDP in part. How I service you, the quality of service you get out of that is part of my success and failure ultimately. And that has nothing to do with engineering. Well, it does, but it's over and above the engineering experience. So how do we do that? We rely heavily on systems engineering. And out of that, it's about how we manage our requirements. And management goes from acquisition of these requirements, prioritization of these requirements, and turning those into potential work. Functional design. What are we going to give you? What this thing we're going to give you, what is it going to do? The feel you have of the telescope comes out of the science data processor. Systems design. What are we going to do to make this thing happen? As part of the things we discuss in there. The verification and validation thereof. How do we know that we gave you what you wanted? Secondly, how do you know we are still giving you what you want 5 years later? So it's an important question to address there. The project management thereof. And I don't even want to call it project management. Risk management, that's what we should call it. And how many things can go bump in the night in the process of realizing the science data processor? We have a very risk-driven approach. Stakeholders. We've got multiple stakeholders internally and externally and internationally, actually. The whole SKA basically rides on us proving that we can deliver. Otherwise, everybody will just pull out of it as a no-hope project. The budget. People who work for us, where do we get them? What kind of people do we get? And then now we're transitioning into operations as we become SARAO. And the question there is, can we operate this thing? The reality is that in our organization right now, or anywhere else in the world, nobody knows from the beginning to if an electron enters the telescope to the time it pitches in that image, nobody knows the whole chain in a single mind. It's the first time this is happening in astronomy, and it's going to get more like this. So can we operate the telescope? If somebody asks a question, can we really answer in detail as to why they're experiencing the phenomenon they're experiencing? Efficiency. How much more money can we go back to the DST and be like, oh, we're running the telescope. Our archive license expired. Oracle is going to lock us out. We need a small sum of $1 billion. It's not going to happen, right? Dependability. If we give you data, can we give you data again and again and again? If you pick up the phone and want to talk to somebody, can you find them? Do we work? Do we pitch every day? Are we Toyotas, basically? That's the question we're asking. So going into systems engineering, what I call requirements management. So here, one of the things we learned through the journey was like, learn from those who have done it, even when no one has done it before. And it's almost like an oxymoron, but the reality is people have done large projects before. CERN, we have a strong relationship with them. NASA have done a lot of exciting projects over a long time. They're sort of over the 50 years or something. They've distilled processes to make your life easy when you engineer what you think you do not know. They have chosen risk-averse approaches, or risk-driven approaches, rather. And that's why they have a significant success rate. 50% rate of landing on Mars. Imagine if ESCOM had a 50% success rate, right? And that's real. It's a real thing that you have to think about, right? Considering where this money comes from. Effective requirements change mechanism. Once you go into systems engineering or any other process where somebody signs a contract, it's very difficult to change things. Whether it's by realizing that you left out something, or what you promised will not work, or it's only going to happen later because something else has happened. Getting that effective, robust, and being dynamic is very critical to your project because it rolls up into stakeholder management. Functional design, a model-driven approach. I think in the project, some of the best money we spent was that we spent it on a lab. And we went crazy in that lab, doing all sorts of things that failed. And by fail, I don't mean like absolute bricks. Some of them, our storage port, for example, we didn't think about the fact that if we have 5 of these things and we put them in a rack and we switch them on, at the same time, they're going to trip the power because their initial draw was so high. Then if we eventually get them up, they vibrate ever so small, but 48 of these things in a box results in screws coming off where you don't want them to come off. So those are the kind of issues that, cooling of that thing. Then we realize that we have to learn aerodynamics. What do I know about aerodynamics, right? Automated documentation. You can literally die by documentation. Save the tree, please. Make sure that you have a dynamic documentation system. How you starting basic behaviors, how you write your requirements, where you write them, how you write your code, how you produce your infrastructure, your artifacts. Make sure that you have a dynamic, automated approach to documentation. Otherwise, you're going to lose. System acquisition management. Systems acquisition is a practice. Learn it. Know it. Know where you should do your R&D. Know what you're building in the context of engineering. If you're building a box, what are you building? Are you building a device? Is it exploitable? Are you going to use it again? What are you doing? Learn your systems acquisition and practice it. System design, like I said, fail very fast, but fail forward. And think. Pencil and paper. It's funny that when you start school, they teach you writing with a pencil and paper, and then they sort of abandon it. But really, they should teach you with a pen and get you into pencil and paper if the outcome we desire is for people to actually stop and think. And question everything. Do not accept. A good example we had there was one supplier where we didn't have national capacity. We made a call for a skill. We didn't get any response. We called a supplier in the US, and they quoted us something ridiculous, like $2 million a year for service. And we simply refused. Like, no, we're not going to pay that at all, ever. And that forced us to go back to questioning, what is it that they're charging us for? A year later, we delivered this system better than anybody had ever developed it before. So that's the kind of attitude you want to adopt. And you want to make that a habit in the organization. Forget about the embarrassment of learning. Forget about those minuscule laws. Because the upside or the downside of failure is you can't even account for it. The absence of the system is worse. Verification to validation. We took a continuous deployment approach. Going back to the budget, we didn't have time to have deployment breaks, test breaks. So we had a continuous deployment approach. It was risk averse. It is what we needed to do. Hard tests. The SDP was one of the systems that stubbornly refused to sign off on any quality document until we could point into the sky and see what we are receiving. It was the only way we could make sure that people don't say things like, oh, we passed by simulation. Oh, I'm sorry. You got a small universe in your... no. Project management. And here, people talk about agile, waterfall. I keep it very simple. The only right way to build a system is to have it built. Just get on with the business of building it and continue. Learn, suffer the embarrassment, grow up, and move fast. Yeah, okay. I talk about the Cult of Done Manifesto. Look it up. People, take care of your people. Spend time and money on your people. Institutional memory is critical. Bring people overseas if you have to learn from them. But for God's sake, take care of your people. We do not have buildings. We don't have anything except what's in people's heads. That's it. Take care of it. Transformation. I can't overemphasize the importance of transformation. This is a South African project. So in operations, I'm running out of time, so I'm going to rush through the remainder of the slides. In operations, the idea here is that, we had to redefine who we are as MeerKAT. Some say we are an observatory, we are buying land. Are we here for people's ego? Are we a facility? Are we there to revive the economy of the Northern Cape? All these things go out as to how we measure, and that drives how we perform. The next one is the African science capacity, what I call African science capacity. We need African science teams. If we don't get them now, we're not going to get them in SKA1. We're definitely not going to get them by 2035, when the full SKA seems to be coming on. And this is a long-term investment in education across all sorts of systems, capacity development. Producing science. People want to win a Nobel out of the SKA, essentially. And that's where we're heading. There's no two-way about it. The question of data. I don't need to say more about data, but the point is we need a concise data management strategy, data analytics. RFI, it turns out that many more people want our RFI, which is the product we thought we did not require. And that's forcing us to relook at how we manage our data as well. The feature of SDP, we are splitting up into several teams: research, science, compute infrastructure, software development, and operations management, so that we remain a rational organization. Supporting the science community. We got an open call out. If you're South African, if you're African, please look up this thing. We just made a call yesterday. We will support you on the science. We will support you on the compute. But please get in there and get involved in our project. Skills development is paramount. And participating in the SKA1 is not a given thing. And to make an announcement, as I was saying, open calls opened yesterday. That's the link. We are also hiring. And I can't finish this without really, and again, thanking the NICU system. Sandren are building our network. CHPC is truly integral to our work. And Teresa will come on board as it matures, because we need a lot more, and we are quite more selfish than a national facility like Teresa right now. So thank you. I don't know if I have time for